So, welcome you back. In the last lecture, we were going through the null function, and we have seen that if we add the null function, there may have certain functions where the Laplace transform of two functions will be same. The consequence we will discuss just after this slide. In this particular lecture, we will start with the inverse Laplace transform. Till now, we have done the Laplace transform of a function. Now, if I know the opposite one, that is, if I know the inverse Laplace transform, then what is the corresponding function for which the Laplace transform is function of s, that we will find out, we will study in this particular lecture. First, see the definition. The inverse Laplace transform, the definition is, if the Laplace transform of a function f t is f s, that is Laplace transform of f t equals f x, f s, then f t is called inverse Laplace transform of f s and is written as capital F t equals Laplace inverse f s. So, therefore, for a function, any function f t, if f s is the Laplace transform, then the inverse Laplace transform of f s is denoted by f t, and it is written as f t equals L inverse f s, where L inverse is called the inverse Laplace transform operator. L inverse is called inverse Laplace transform operator. This one, I will not go to this. Now, you see this theorem, Larch theorem, it says that if we restrict ourselves to functions f t, which are sectionally continuous in every finite interval 0 to n and is of exponential order alpha for t greater than n, then the Laplace inverse Laplace transform of f s, that is Laplace inverse f s equals f t, is unique. Means, if I have the Laplace transform of a function, then the Laplace inverse Laplace transform of that function will be unique if we restrict the functions to this only, that is, if we do not consider the null functions. And here you come the other form of Larch theorem, that is, if f 1 t and f 2 t are two functions having the same Laplace transform f s, then f 1 t minus f 2 t equals n t, where n t is a null function. That is, an inverse Laplace transform is unique except for addition of a null function. So, if the function is not a null function, always the inverse Laplace transform will be unique. And so, let us go to the some properties. The first property is the linearity property. Just like in the Laplace transform, we had the linearity property, in inverse Laplace transform also we have the linearity property. If f 1 s and f 2 s are Laplace transform of f 1 t and f 2 t respectively, then Laplace inverse C 1 f 1 s plus C 2 f 2 s, this is equal C 1 Laplace inverse of f 1 s plus C 2 Laplace inverse of f 2 s. Let us see the proof of this one. In the proof, so here Laplace transform of C 1 f 1 t plus C 2 f 2 t, this equals, we know that C 1 Laplace transform of f 1 t plus C 2 Laplace transform of f 2 t, this we know it, already we have done earlier. Or you can say C 1 f 1 s, if Laplace transform of f 1 t is f 1 s plus C 2 into f 2 s, where f 2 s is the Laplace transform of f 2 t. So, we can write down this thing. Therefore, we can say that C 1 f 1 t plus C 2 f 2 t, this is equals Laplace inverse of C 1 f 1 s plus C 2 f 2 s. This you can write down always. which implies that from here you can write down C1 into Laplace inverse of F1s, F1t we are writing, plus C2 into Laplace inverse of F2s. This is equals Laplace inverse of C1 F1s plus C2 into F2s. This we are writing over here. So, this we are showing that Laplace inverse of C1 F1s plus C2 F2s, this is nothing but C1 Laplace inverse of F1s plus C2 Laplace inverse of F2s. Since F1t is nothing but the Laplace inverse of F1s and F2t is the Laplace inverse of F2s, and therefore, this completes the proof of your theorem. So, let us go back to the other one, that is, this is the Laplace transform of this, and from here you are writing C1 F1t plus C2 F2t equals Laplace inverse of C1 F1s plus C2 F2s. From here you are writing this point, the last line which already we have written over here. Let us take an example how to find out the Laplace inverse of this function, which is a function of s. This function we can write down, your function is Laplace inverse of s by s square plus 2 plus 6 s by s square minus 16 plus 3 by s minus 3. So, using the linearity property, I can write down Laplace inverse of this is s by s square plus 2 plus 6 into Laplace inverse of s by s square minus 16 plus 3 into Laplace inverse of 1 by s minus 3. Now, please recall s by s square plus 2 is the Laplace transform of which function? You know it very well, that is cos of, this is plus 2. This plus 2, if you write it as root 2 whole square, say, this plus 2 you can write down as root 2 whole square. So, that s square, s by s square plus s square, s by s square plus s square is the Laplace transform of the function cos a t. So, therefore, Laplace inverse of s by s square plus s square you can write down cos of root 2 t plus 6 into s by s square minus 16. This again you can write it as s by 4 square. So, this is nothing but cos hyperbolic 4t. Please remember that for cos hyperbolic a t, the Laplace transform of cos hyperbolic a t is s by s square minus s square, and this is easier one by s minus 3, that is e power 3 t. So, like this way. So, once I know the inverse Laplace transform, I can find out, once I know the Laplace transform of a function, using the inverse Laplace transform, I can tell what is the corresponding function, and using linearity property, effectively we are finding out this particular value of the function. So, you are just getting this value cos of root 3 t 6 cos hyperbolic 4 t plus 3 e power 3 t. For your easy remembrance, just I have given a set of Laplace transforms and what is the corresponding function. Like if 1 by s for the function 1 Fourier transform, Laplace transform is 1 by s. If the function is t power n by factorial n, you know the corresponding function is 1 by s to the power n plus 1, t to the power where n belongs to natural number, t to the power n by gamma n plus 1. For this function, Laplace transform is 1 by s to the power n plus 1, where n is greater than minus 1. For if it is function is e power a t, the Laplace transform is 1 by s minus a. If it is 1 by a sin a t, then the corresponding transform is 1 by s square plus a square. If it is cos a t, s by s square plus a square is the Laplace transform. If it is 1 by a sin hyperbolic a t, it will be 1 by s square minus 1 by s square minus s square, and if it is cos hyperbolic a t, in that case it will be s by s square minus s square. So, for your ready reference, I have just given the Laplace transform and the corresponding functions whose Laplace transform. This table you can use for ready reference. Now, let us try to find out the Laplace transform, inverse Laplace transform of this particular function. For inverse Laplace transform of this function, Laplace inverse of 5 by s square plus root over s minus 1 by s whole square minus 7 by 3 s plus 2. So, this I can first write down Laplace inverse of 5 by s square plus this I can break it s minus 2 root s plus 1 by s minus 7 by 3 s plus 2. Once I am writing this, now I can break it into parts, that is here 5 by s square is there, another one will be s square. So, if I break it into two parts, here it will become 5 plus 1 6 Laplace inverse of 1 by s square plus Laplace inverse of 1 by s minus 2 Laplace inverse of 1 by s to the power 3 by 2, 1 by s to the power 3 by 2 minus 7 by 3 Laplace inverse of 1 by s plus 2 by 3. Actually, I have written it in such a fashion, so that directly now you can write down corresponding function. Just like if you see 1 by s square is the Laplace transform of which function, that I have to write down. So, 1 by s square is, if you take the function t whose Laplace transform is 1 by s square. Therefore, inverse Laplace transform of 1 by s square is 6t, 6 into t. For 1 by s it is 1 minus this will become 4 into root over t by pi minus 7 by 3, this is e power minus 2 by 3 into t, e power minus 2 by 3 into t. So, for this particular inverse Laplace transform, corresponding function is this one 60 plus 1 minus 4 into root over 2 by pi minus 7 by 3 into e power minus 2 by 3. So, like this way we try to find out the solution of these equations. So, Laplace inverse of this is this one, and from here you are getting the corresponding results. So, by this way, if you have been provided with the inverse Laplace transform, then I can find out the corresponding function. Now, if you recall, in Laplace transform also we studied various properties which helped us to solve the problems or to find out the Laplace transform of various functions quickly. Similar properties are available in inverse Laplace transform also, and using the properties of inverse Laplace transform, we can very quickly find out the function whose inverse Laplace transform is provided to us. The first property is, if Laplace, which we call as first translation or shifting property, if Laplace inverse of f s equals f t, then Laplace inverse of f of s minus a equals e power a t into f t. That is, if s is shifted from s to s minus a, then e power a t will be multiplied in the function. So, for the proof of this one, your f s we know it 0 to infinity e power minus s t into f t dt, we know this thing. Therefore, from here you can write down f of s minus a will be 0 to infinity e power minus s minus a into t into f t dt. S is replaced by s minus a. So, that this equals, again you can write it 0 to infinity e power minus s t, you can put it here, and inside bracket you can write down e power a t into f t. This I am writing here dt. So, this is nothing but again from the definition of Laplace transform, the Laplace transform of this thing e power a t into f t. So, therefore, this equals Laplace transform of e power a t into f t. Therefore, I can say that Laplace inverse of f of s minus a, this is equals e power a t into f t. So, this completes the proof that if Laplace transform of f t is small f s, then Laplace inverse of f of s minus a is equals to e power a t f of t. So, just I am giving the proof here again for your f of s minus a is this, which is we can write down 0 to infinity this, and which is nothing but Laplace transform of e power a t into f t, which completes the proof that Laplace inverse of f of s minus a equals e power a t into f t. Next property is, if your second property which we call as shifting property, this is also translation property. Here t is being shifted from t to t minus a. If we have Laplace inverse of f s equals f t, and if we have a function g t such that for t greater than a, value of g t is f of t minus a, otherwise it is 0, then Laplace inverse of e power minus a s into f s equals g t. Laplace inverse of e power minus a s into f s equals g t, that is f of t minus a for t greater than 0 and 0 for t less than 0. For the proof of this, we have to start with Laplace transform of the function, that is Laplace transform of the function g t, which is equals to 0 to infinity e power minus s t into g t dt. As usual, we have written this, you can break it into two parts, that is 0 to a the function plus a to infinity the other function, and 0 to a this function, this value of the function g t is 0. Therefore, this term will vanish over here. So, this equals directly you can write down a to infinity e power minus s t into f of t minus a dt, because g t equals f of t minus a for t greater than a. So, we are getting this function a to infinity e power minus s t into f of t minus a, this one. Now, if you substitute t minus a equals say u, if we substitute t minus a equals u, the lower limit at t equals a u will be 0, upper limit will become infinity e power minus s into u plus a into f of u du. You will get f of u into du, but the limit has been changed from 0 to infinity. At t equals a, u is 0, and t equals infinity, u is equals to infinity. So, that e power minus a s you can bring outside, 0 to infinity e power minus s u into f u du. And what is this one? This term is nothing but the Laplace transform of f u, because 0 to infinity e power minus s u into f u. So, you can write down e power minus s into f s. So, Laplace transform of g t equal to e power minus a s into f s, or in other sense you can write down g t equals Laplace inverse of e power minus a s into f s, which completes the proof of your theorem. I hope it is clear to you. So, your just the proof again you see here, I am breaking it into two parts, 0 to a to infinity, the first integral vanishes. So, that it becomes a to infinity e power minus s t f of t minus a dt, and By substituting t minus a equals u, you are getting this integral which I have shown already. If you are bringing e power minus a s outside, this integral is nothing but the Laplace transform of the function f u, which is f s. So, that you can write it as e power minus a s into f s. So, that you can write down g t equals Laplace inverse e power minus a s into f s, which completes the proof of this particular theorem. Now, next theorem is change of scale property. It says that if Laplace inverse of f s equals f t, then Laplace inverse of f of a s, that is Laplace inverse of f of a s just 1 minute. Laplace inverse of f of a s equals 1 by a f of t by a. That means, whenever you are multiplying your by some scalar property a with the parameter s, that is s is replaced by a s, then the function will be 1 by a into f of t by a. For the proof, your f of a s, this is nothing but 0 to infinity, since it is a s there. So, e power minus a s t into f t dt. On this, if you substitute, say a t equals x. If you substitute a t equals x, this will become 0 to infinity, it will remain same a t. So, 1 by a will come e power minus s x into f of t is x by a into dx. Once I am substituting this as a t equals x. This integral equals, you can write down 1 by a going outside, 0 to infinity e power minus s x into f of x by a into dx. So, this again x can be replaced by t, that is 1 by a 0 to infinity e power minus s t into f of t by a dt we can write down, and which is nothing but the this integral again you see nothing but the Laplace transform of the function f of t by a. So, that I can write down 1 by a into this one f of t by a, sorry, this is wrong, this will be equals to 1 by a into Laplace transform of f of t by a. So, once I am getting this, therefore, we can say that Laplace inverse of f of a s, if I take Laplace inverse of f s is equals to 1 by a into f of t by a, which completes the proof of the theorem. So, therefore, please note that if Laplace transform of f t is f s, then Laplace inverse of f of a s will be equals to 1 by a f of t by a. Just see the proof once. F of a s is this. So, that by substituting a t equals x, you are obtaining this one. From here, you can write down 1 by a 0 to infinity this. The integral is nothing but f of t if we convert, and it is nothing but the Laplace transform of f of t by a. Therefore, Laplace inverse of f of a s is equals to 1 by a f of t by a, which completes the proof of the theorem. Now, let us see one example. We want to find out the Laplace inverse of this function 3s minus 2 by s square plus 4s plus 20. To find out the solution of this, Laplace inverse of 3s minus 2 divided by s square minus 4s plus 20. So, basically I have to bring it into linear scales, that means I have to break it into parts, so that I can write it in some other way. So, Laplace inverse of this I can write down 3s minus 2 divided by s minus 2 whole square plus 16. Please note that I have the forms of s by s square plus s square or a by s square plus s square, something like this. So, basically whenever we try to find the solution of inverse Laplace transform, the function of s, I should bring it in some forms whose Laplace transform is known to me. That should be the basic aim whenever I try to solve a problem. Please note this one, that if I try to solve a problem, then I should know the inverse Laplace transform or the Laplace transform of a function whose Laplace transform is known to me. So, I will bring it to some common things. For that reason, this denominator we are breaking it in the form of a square plus a square form, and this equals, you can write down Laplace inverse of 3 into s minus 2, I can make it here, s minus 2 whole square plus 16. So, this was 3 x minus 6 I have made. So, I have to make plus 4. So, it is s minus 2 whole square plus 16 I can write down. Again this 3 will come outside. So, this will be basically s minus 2 by s minus 2 whole square plus 16. This 4 can go out. So, that it will be 1 by s minus 2 whole square plus 16. So, effectively it becomes 3 into Laplace inverse of s minus 2 by s minus 2 whole square plus 16 plus 4 into Laplace inverse of 1 by s minus 2 whole square plus 16, and this is nothing but 3 into s minus 2 by s plus 6 s minus 2 by s minus 2 whole square plus 16. L inverse this directly I cannot bring into the form, because here you have s minus 2 in both side, therefore, e power will come. So, this is actually 3 e power 2 t into s by this form. So, it will be cos 4t. I am directly writing this one, actually this minus 2 also will go on that side, plus e to the power s by 4 square, but it will become sin 4 t, because it is 1 by this 4 is there. So, I have to multiply over there and I will get e power 2 t into sin 4 t. So, effectively if I have a function, I will try to solve it in such a fashion, try to find out the solution in such a fashion, or I will try to put it in such a function whose inverse or whose Laplace transform, inverse Laplace transform is known to me. So, just quickly if I see this one, Laplace inverse of this I am breaking into these parts. This equals, again you can write down 3 Laplace inverse of s minus 2. This equals actually 3 e power 2 t into s by s square plus 4, and 4 e power 2 t, which I have not written there, using the property of inverse Laplace transform. I am just breaking it, this part I am breaking it here, that e power, if I know the f of a s, then if I multiply by a s by a, that property I am using here, and I am getting Laplace inverse of this, and from here I can obtain the desired solution. My next example is Laplace inverse of s minus 1 by s plus 3 into s square plus 3 s plus 2. So, Laplace inverse of s minus 1 by s plus 3 into s square plus 2 s plus 2. This is actually, if you see, I have to break it, this denominator is having 2 factors, but whenever denominator is having 2 factors, using the mechanism, normal mechanism, this equals a into a s plus b by this, I have to break it into function such that in each denominator there will be only one factor, not more than one factor. So, using that trick, directly I am writing this equals, we can use it as minus 4 by 5 into s plus 3. Again I am skipping this one, this we have done in the case of differential equations also to find the solution, and 5 into s square plus twice s plus 2 we are writing. So, now this I can write it as 4 by 5 can come outside, Laplace inverse of 1 by s plus 3, whose Laplace transform you know it, plus 1 by 5 Laplace inverse of this. You see, this will be 4 into s plus 1, 4 into s plus 1. So, 4, so minus 3 will be added, 5 into s square plus 2 s plus 2. That means, this part again I have to break it into two parts. This you know 4 by 3 into e power minus 3 t 1 by s plus 3. So, corresponding function is e power minus 3 t. For the function e power minus 3 t, Laplace inverse is Laplace transform is 1 by s plus 3. This equals, you can write down 1 by 5 and you can e power s plus 1 is here. So, e power minus t, again I am using the property here and I can write down Laplace inverse of 4 s by s square plus 1 minus 3 by s square plus 1. So, that actually this I have done by this I have written actually s plus 1 whole square plus 1. For that reason, actually e power minus t, s is shifted to s minus a. So, e power minus t is coming over here, and using this one I am breaking it into two parts, 4 s by this minus 3 by this thing, 5 into this one. So, now I know the function for inverse Laplace transform of this function also, 1 by 5 e power minus t into this is nothing but s by s square plus 1. So, corresponding function is cos t minus 3 into 1 by s square plus 1, that is sin t. So, if you see here, the trick is something lies like here. Whenever I have a product of two functions, then I have to break it in such a way that on the denominator always I need one function, and in the denominator if I have something like this s plus 1 whole square or like that, then using the property I can write down this as e power something into L inverse of, I can break it into parts. So, like that way I can obtain the solutions. In the next lecture we will go through some more examples.